Very good morning to all. Let us enter into the fourth day of our binary class. Mm. Already we have discussed something about the hemoglobin, myoglobin, hemerythrin, hemocyanin, and sulfur proteins, blue copper proteins, and some of the enzymes we have discussed. Blue copper proteins also I think we have discussed, and catechol oxidase and tyrosinase. Uh, some of the type 2, type 3 copper containing enzymes also we have discussed. Initially we have discussed something about the metal ions and their storage and transport in the uh, living organism, how they are entering from outside to inside the cells, and what is the mechanism of transportation, how the biomolecules are involved in their transportation and everything we have discussed. Do you have anything to clarify in the above topics, or shall I move on to the cytochromes now? If you are having any questions or any other questions from any other bank, if you are having, then if you are having any doubt about related topics, then please ask now. Or shall I move on to the cytochromes? Shall I move?
Yes, sir.
Yeah, cytochromes. Cytochromes is another heme containing protein that is also involved in. There are several kind of cytochromes are there. Their functions are entirely different from each and every places. Generally, if you are speaking cytochromes, they are act as the electron transferring agent. Cytochrome C is there. Cytochrome C oxidase is there, and cytochrome P450 is there. They are entirely different their biological role. But in general, cytochrome, if you are speaking, they are mainly involved in electron transfer. How many electrons they can transfer? They can transfer only one electron. Where cytochrome is present? Cytochrome presence எங்கப்பா இருக்கு? எங்க present ஆயிருக்கு? Where you can see the cytochromes? செல்ஸ்ல எங்கப்பா cytochromes இருக்கு? Mitochondria. So mitochondria என்ன நடக்கும்? What is the biological process which is taking place in mitochondria?
It is a powerhouse.
Powerhouse.
Energy storage.
Energy storage. Okay. So food metabolism will takes place at the cytochromes. So metabolism, respiration, during the respiration process, the inhaled oxygen is converted into water. So the O2 is reduced. O2 will be activated and reactive oxygen species will be generated. Then further it will be evolved as a H2O. Okay. So பாடிக்கு தேவையான more than 60% of வாட்டர் ஃபுல் எதுல இருந்து வந்துரும்? உங்களுக்கு ரெஸ்பிரேஷன் ப்ராசஸ்ல இருந்தே வந்துடும். ஏன்னா வாட்டர் எவ்வளவு ஆக்சிஜன் நம்ம எடுத்துக்கிறோமோ ஒவ்வொரு நாளைக்கும் அந்த ஆக்சிஜன் ஃபுல்லுமே என்னவா மாறணும்? வாட்டரா மாறணும். So they are present in the mitochondria. This is the cross section picture of mitochondria. So mitochondria is nothing but where the food metabolism respiration process will take place. If you are seeing, it is having a folded inner membrane and a outer membrane. There is a space between both the inner membrane and the outer membrane, that is known as intermembrane space. So here you can see ribosomes and other small components which are present in the mitochondria. You can able to see. So this is the membrane. In between these two, you can able to see the arrangement of the electron transferring agents which are involving in the your respiration process. It is also a heme protein, as we said. So it is definitely colored in nature. If you are seeing, it is act as a one electron carrier. So facilitate, what is its role? It will facilitate the transfer of electron. In photosynthesis also we have seen cytochromes. I think in here also you can able to see cytochrome. In human beings also cytochromes also present. Cytochrome will act as a mediator to transfer the electrons. Here the active site is nothing but heme group. It occurs where it will occurs in almost all the eukaryotes organisms, and some prokaryotes also having cytochromes. Photosynthesis என்ன பண்ண நடக்கும்? O2 will be reduced to water, whereas in the aerobic respirations la வந்து sorry in photosynthesis la வந்து O2 will be produced from water, whereas respiration process la O2 will be reduced to water, as we said already. So this is the equation which shows that upon oxidation as well as reduction, so that means there is that acceptance as well as giving up of the electron. So the oxidation state of cytochromes also changing from +2 to +3. So in the oxidized form, iron is in the +3 oxidation state, whereas in the reduced form, iron is in the +2 oxidation state. So in this, redox couple is reasonable for is the main reason for the transportation of electron. So this is the structure that we have to recall once again, as we have already seen in so many cases. Here also we are going to see the such kind of basic fundamental active state structure, which was derivatized by some other functional groups, and there are some functionality difference also you can able to see in the case of various types of cytochromes. See, structural diversity, if you are seeing cytochromes vary in the nature of their heme group. So depending upon the heme group substituents, we can classify them into several categories. So first one is a cytochrome A. Cytochrome A means it is containing heme A structure. The active site is nothing but heme A. So we were well known that in this heme A there is a long hydrophobic tail of isoprene unit is attached to the porphyrin ring. So here in previous case in hemoglobin, what we have seen, the hemoglobin is having a heme B structure. Heme B structure is having 4-methyl, 2-vinyl and 2-propionic acid substituent. Here you can see a long hydrophobic isoprene tail which is attached to the porphyrin as a one of the substituent. Here you can able to see, instead of one methyl group, you can able to find out a formal functional group in the ring structure. So this is what we have discussed so far. Here you can be able to see the one vinyl group. So one more vinyl group is undergoing some addition reaction with the some other long alkyl chain unit. So it is converted, it is having a hydroxy functional as well as a long isoprenoid tail. This tail is providing the hydrophobic environment for the particular active site. Here the one methyl group which is adjacent to the your propionic acid is having formal functional group. Aldehydic functional group is present. Here total of 3 methyl group, 2 propionic acid group, 1 long isoprenoid tail and 1 formal group and 1 vinyl group. Here you can see some more additional substituents in addition to that of the methyl, vinyl and the propionic acid derivative. So if you are having the long isoprenoid unit along with the formal group, then the heme ion complex of the such porphyrin is known as heme A. Heme A is present in the cytochrome A's. The apical ligands may be different. Here you can see it is involving in electron transfer. It is not a coordinatively unsaturated complex. It is a coordinatively saturated complex. Iron will adopt a octahedral geometry in the case of electron transferring function, or in tetrahedral. Tetrahedral environment also the coordination is saturated around the ion set. In octahedral there is no further addition of the ligands or something will takes place. Cytochrome B, it is having heme B structure. As we well known about the heme B structure, it is the combination of iron 2 and protoporphyrin 9. That is nothing but what we have seen in the case of the hemoglobin. So we are familiar about with this. So 2 propionic acid substituents. Wait a minute. Yeah, 2 propionic acid substituents, 4 methyl groups and 2 vinyl groups. This is the one we well known about those things. It is complexed with the iron in the +2 oxidation state. That is known as heme B structure. Cytochrome C, it is a heme C structure is present in the active site. Heme C is nothing but the protoporphyrin 9 in which two vinyl functional groups are covalently connected with the protein residue via cysteine moiety. What does it mean? The vinyl CH double one CH2 group is undergoing addition reaction with the vinyl substituents of the uh, addition reaction with the cysteine thiol group. So you can able to see here. See nicely. Previously, what we are having only the vinyl substituent. So the methyl group, that cysteine sulfur, which undergo which will attack the CH bond, CH carbon, and the CH from that the double bond will shift to the CH2 group. So the proton which is associated with the cysteine sulfur will be transferred. This is a thiol. Now it is converted into thioether. So this is the only protein in which it is undergoing a covalent interaction with the protein structure. Previously, there is no covalent interaction. So for only the apical ligand will undergo coordinate bond formation, and thereby the heme unit will undergo contact with the your protein structure. But here the protein is directly contacting with the active site structure. This is the beauty of the cytochrome C. Vinyl substituents of the protoporphyrin 9 form covalent thioether linkage with the cysteine residue of the protein. This is what we have already said. See, nicely it is forming a covalent linkage. Here that is shown as a yellow colored one. Axial ligands in cytochromes. As we said, these molecules all are coordinatively saturated. Unlike in hemoglobin is having the square pyramidal geometry before oxygen attack. So one vacant site is left free for O2 attack. But here there is no such kind of small molecule interaction is going to happen. It is only acting as an electron transfer agent. So it should not having any vacancy. If you are seeing, this is the structure of the cytochromes, various cytochromes with apical ligands. So this is a porphyrin unit which was suitably functionalized, and the apical position in cytochrome A and cytochrome B both are having histidine imidazole nitrogen only. So 6 nitrogen donors are surrounding the iron, whereas in the case of cytochrome B also we are having 6 nitrogen donors. 2 is coming from the protein residue and 4 nitrogens are coming from the porphyrin pyrrole nitrogens. The beauty of the cytochrome C is here it is having one apical ligands are not same. One is histidine imidazole nitrogen, another one is a methionine thioether group. This is the protein donor. Protein might is histidine as well as methionine. If you are seeing, the imidazole nitrogen will undergo interaction. This is a heterocyclic nitrogen will undergo interaction upon bond formation. Here the thioether sulfur will undergo the covalent bond formation, coordinate bond formation with the iron center. This protein structure is shown here for just to recall. So what is the optical spectral characteristics of the various cytochromes? So due to the presence of various porphyrin substituents as well as the different axial ligands, their lambda max value also shifted to some reasonable values. You can see cytochrome A is having 600 nanometer, whereas the cytochrome B is observing around 560 nanometer, 40 nanometer difference you can able to see. Whereas cytochrome C, if you are seeing only 550 nanometer, there are only 10 nanometer difference occurring between the cytochrome B and C, but they can easily be distinguished by means of the data, whatever we are having. Okay. Any doubt?
No, sir.
Okay. Redox potential value, if you are seeing the standard redox potential of the oxidized and reduced form of the cytochromes are shown here. In eukaryote, if you are seeing, cytochrome A is having higher positive potential, whereas cytochrome B is having less positive potential than that of the cytochrome A as well as cytochrome B. If you see, in the case of cytochrome C, it is having the second largest positive potential value, whereas cytochrome B is having less positive potential value. So what does it mean? If they are having higher oxidation potential, what would happen? Lower oxidation potential, what would happen? Let us see here. The direction of electron flow also changes. Cytochrome B can transfer electron to the cytochrome C, then only it will transfer to cytochrome A. So higher positive means that can readily accept the electron. Higher negative means it will readily donate the electron. So the electron will flow from B to C and C to A. In this direction only the electron can be transferred. From cytochrome A to C, it won't transfer. And the reverse reaction is not happening. Since it is having higher positive potential, it is having a tendency to accept the electrons, not to donate that much easily. If the next one, the molecule which is present in the electron transport chain, which is having higher positive potential, that will definitely takes up the electron from cytochrome A. But the reverse reaction is not that much favorable. So already we have seen cytochromes are coordinatively saturated. So what is the main reason for such kind of octahedral environment around the iron center? Is there any special reason is there for that? Is there any reason? Why in general the electron transferring enzymes are preferring the coordinatively saturated environment? Is there any special reason is there? Anybody? Am I audible? Yeah, am I audible?
Yes, sir.
ஏன் கோஆர்டினேட்டிவ்லி சேச்சுரேட்டடாவே இருக்கு எல்லா இதுமே வந்து எலக்ட்ரான் டிரான்ஸ்ஃபரிங் புரோட்டீன் எல்லாமே
Sir,
The stability பொறுத்து.
to maintain structural stability, sir.
ஸ்ட்ரக்சரல் ஸ்டெபிலிட்டி வேணும் ஏன்னா வந்து டியூ டு த ரெடக்ஷன் அண்ட் ஆக்சிடேஷன் வந்து ஸ்ட்ரக்சர் வந்து லார்ஜ் ரீஆர்கனைசேஷன் போகக்கூடாது. அது இன்டர்மீடியட் ஜாமெட்ரி இருந்துச்சுன்னா என்ன ஆகும், அடிஷன் ஆஃப் த லிகாண்ட் அண்ட் டிட்டாச்மெண்ட் ஆஃப் த லிகாண்ட் வந்து நடக்கக்கூடாது. இங்க வந்து என்ன ஆகணும், இட் ஷுட் ஃபார்ம் அ கோர், the core should retain its geometry before and after electron transfer. Then only the geometrical reorganization வந்து என்ன இருக்கும், ரொம்ப ரொம்ப மினிமமா இருக்கும். So the energy can fully utilized for the electron transport only. That is the ultimate aim of the nature, to do all the function. In almost all the cases, if you are seeing the electron transfer or activation or some other things, whatever you are seeing, there is not much structural changes associated with such kind of biological process. All the chemical reactions whatever taking at the biological system is mainly follow the route which having low activation barrier. So the iron in the cytochromes having they are alternating between the iron 3 to 2 that we have already said. So one case if you are seeing the oxidized form is low spin iron 3 with a d5 configuration, and it is a paramagnetic species also. Whereas in the case of the reduced form also maintaining the low spin state. But it is somewhat different from what we have seen in the case of iron sulfur proteins. Iron sulfur proteins என்ன பார்த்தோம், the spin state வந்து என்னவா இருந்தது, high spin stateலயே இருந்தது. There is no change in spin low spin state. But here பாத்தீங்கன்னா the iron is put in the low spin environment only. It is entirely different. Two cases are entirely different. One caseல என்ன பார்க்குறோம், iron வந்து high spinல இருக்கு, both oxidized and reduced form. In another caseல வந்து பார்க்கும்போது எப்படி இருக்கு, low spin state which is maintained in both as well as oxidized and reduced state. So அப்படிங்கும் போதுல வந்து the reduced form is diamagnetic in nature with there is no unpaired electrons. All the electrons are paired in the T2G level itself. Since the iron remains in low spin, electron transfer is greatly facilitated. That means that electron transfer, upon electron transfer, there is no structural reorganization takes place. Previously, in hemoglobin, what happened? When the spin state is changing, at the time the coordination environment is slightly perturbed, due to which what is happening, there is a structural reorganization in the protein is taking place. So that is the ultimate aim of the nature. Here it should not spend much amount of energy for the process. So the electron transport chain is occurring inside your mitochondria. There is the complexes are involved in found in the inner membrane. They are present in the inner membrane. The electron transferring agents are present in the inner membrane, the folded region of the inner membrane. There are 4 complex systems which are present in the electron transport chain, which can also pump the electrons as well as proton to the ATP synthase molecule. சரியா? ஸோ இங்கே வந்து என்ன ஆகுது, இந்த எலக்ட்ரான் டிரான்ஸ்ஃபர் பற்றி சொல்கிறோம். எலக்ட்ரான் டிரான்ஸ்ஃபர் நடந்து ரெஸ்பிரேஷன் மூலமாக we are gaining the energy by metabolizing the food. ஸோ அதுக்கு வந்து என்னது, இந்த எனர்ஜியை ஸ்டோர் பண்ணுறதுக்கு தான் இங்கே ஏடிபி சிந்தேஸுங்கிற என்சைம் ஃபேக்டர் வந்து ப்ரெசென்ட் ஆயிருக்கு. தட் என்சைம் கோஃபேக்டர் வில் utilizes the energy and it will synthesize the ATP. These are the components which are present in the electron transport chain and their redox potentials are shown here. So they are having a diverse range of redox potential from approximately +1 to -0.3. This is the way. So the electron can easily transfer from here to here and here to here, here to here, here to here. In the downward direction only electron can move, not in the upward direction. Since it is having a positive potential, so it can accept the electrons only. So this is the way how the 4 complex systems are arranged inside the inner membrane of the mitochondria. So this is the overall transport chain. The complex one is composed of NADH and FMN, and complex 2 is nothing but your succinate to fumarate converting cofactor along with the iron sulfur protein and the FADH. So these will transfer as well as the proton as well as the electron. So here the redox mediator quinol is present. Quinol will act as a redox partner and it will undergo quinone to quinol. So this will transfer the electron to the cytochromes. This is the way, as already we have discussed, cytochrome B to C, C to and A. In that way only the electrons will be transferred. This is cytochrome C A3. This is nothing but your cytochrome C oxidase. This is the one which is responsible for the reduction of molecular oxygen into O2. Here it is a couple of 2 reaction centers. One is having iron porphyrin unit, another one is a copper containing active site. So they will couple together and they will facilitate the O2 reduction. This system is known as complex 4. First one is the redox of NADH at complex 1. Electrons goes to the complex 1. 4 protons are pumped from the matrix to intermembrane space. So 1 electron வந்து என்ன ஆகுது, இங்க வந்து electrons வந்து first NADH ல இருந்து complex போகும்போதுல வந்து 4 protons are pumped into the intermembrane space க்கு வந்து ரிலீவ் ஆகுது. ஏன்னா எலக்ட்ரான் டிரான்ஸ்ஃபர் எப்பெல்லாம் நடக்குதுன்னு சொல்றோமோ நேரமே it is also parallelly the proton transfer will also occur. That is the important thing, we should note that. இது எங்க நடக்குது, மெம்பரேன் புரோட்டீன்ல தான் இருக்குன்னு சொல்றோம். மெம்பரேன்ல நடக்கும் போதுல வந்து என்ன பண்ணுது, ஃபர்ஸ்ட் NADH வந்து proton transfer பண்ணும்போதுல meanwhile it is under ejecting 4 electrons to the intermembrane. இப்போ டோட்டலா பார்த்தோம்னா காம்ப்ளெக்ஸ் 1ல இருந்து ஒரு இது வருது, 4 proton வருது, காம்ப்ளெக்ஸ் 3ல இருந்து 4 protons போகுது, as well as வந்து காம்ப்ளெக்ஸ் 4ல இருந்து 2 protons போகுது. டோட்டலி எத்தனை protons வந்து intermembrane போயிருக்குன்னா 10 protons are ejected to the intermembrane space. Finally the O2 is converted into H2O and the energy is stored in the form of ATP. So what is the role of FADH2 and NADH? They will act as a electron donors, as well as if they are active, they are donating the electron, means meanwhile the protons also will be produced. This is the structure of nicotinamide adenine dinucleotide. It is having dinucleotide, that is only This is the one. This is the another one. Nicotinamide is shown here. This is a base and sugar and phosphate. This is also a base and sugar and phosphate. It's a dinucleotide is present. So it is having protons. These protons will be transferred during which the electrons also transfer into the catalytic cycle. This is the structure of flavin and mononucleotide. It is in the oxidized form. It is the reduced form. If you are seeing in the reduced form, there are two protons are there. So it can donate two protons as well as two electrons. So what is happening? NADH bind to the very fast complex of the electron transport chain by interacting with the prosthetic group of flavin mononucleotide. This is what we have shown here. NADH is bound with the flavin mononucleotide and it will donate the electrons immediately, and it will NADH will act as a reducing agent. So what would happen? FNMM picks up the electron and undergo reduction. So the reverse reaction will take place. So here the forward reaction will take place. So the electrons as well as protons donated by the nicotinamide will undergo the reduction of the C double bond N. So it will be reduced and it will, and here you can see it will follow the radical mechanism. So one electron will be transferred here and one more electron will come from here. So automatically it will having a one electron. So it will two electrons here, total of two electron and two protons are supplied. So that is those electrons and protons are more than enough to form a NH bond. So already it is having single electron, so it will takes up one electron and one proton and it will add it to here. Here also the same thing will happen. This is how the way the electrons and protons are transferred via the redox partners. So what would happen once the FNM picks up the proton as well as electron? It will transfer to the electrons to the iron sulfur clusters which are present in the next step. So what would happen if these protons are not pumped into the intermembrane? The answer is extremely simple. So whenever the electron transferring taking place, at the time the protons should also be transferred. Otherwise what would happen? There is no flow of electron. ஏன்னா வந்து அங்க பிளஸ் மைனஸும் வந்து என்ன ஆகணும், காம்பன்சேட் ஆகணும். போற சார்ஜ் வந்து டிரான்ஸ்ஃபர் ஆகும் போதுல வந்து everything should be compensated. Yes. Otherwise electron transfer will be stopped. The transfer of protein and the electrons are interlinked. The event must happen together. So whenever they are parallelly occurring, at the time only this process will be more facile and it will be facilitated. Next step, what is happening? From FADH to iron sulfur protein, the electrons are transferred. So where it will be transferred to the complex system, it will transfer to the quinol moiety. So next step is the complex 2. Complex 2 is nothing but your fumarate succinate redox partner along with the FADH2. So this coenzyme Q picks up the electron from the complex 1 and 2 and transport to the electron complex 3. So this is the complex system 2. This will also transfer protons, electrons, whereas the complex 1 also transfer the proton and electrons. This is the redox partner. This quinol and quinone redox couple is connecting the bridge between the cytochrome C as well as the electron sources. So from the quinol itself, the electrons are transferred to cytochromes. This is the flavin adenine dinucleotide. This is the structure of the flavin adenine dinucleotide. It is a flavin moiety. It is adenine and it is having disaccharide which are connected via two phosphate esters. Here also it is having a number of reducing sites. It is also having two reducing sites. This is a ubiquinone. This is the redox partner what we have seen. This is the quinol Q. Q is nothing but the ubiquinone. Ubiquinone structure is shown here. It will also transfer two electrons as well as two protons. So the quinol to quinone conversion is accomplished by the transfer of two electron as well as two proton. So generally biological system, the hydroxyl group rich aromatic ring systems are we well known about those things. They will immediately undergo enol to quinone formation by simple oxidation. ஏன்னா phenolic compoundலாம் நீங்க ஓப்பன்ல வச்சீங்கன்னா என்ன ஆகும்? quinola that will be quinone formation வந்து என்ன பண்ணும்? ஈஸியா வந்து facilitate பண்ணும். Since these processes are require only minimum amount of energy, so the conversion into alcohol to ketone form is more facile. Complex 2 is a parallel electron transport pathway to complex 1, but unlike in complex 1, no protons are transferred to the intermembrane space in this pathway. அதில் ஆல்ரெடி நம்ம பார்த்தோம் இல்லையா, இந்த இன்டர்மெம்பரேன் ஸ்பேஸுக்கு வந்து காம்ப்ளெக்ஸ் 2ல இருந்து வந்து என்ன போறது இல்லை, ஒன்லி எலக்ட்ரான்ஸ் மட்டும்தான் போகுது. தேர் இஸ் நோ டிரான்ஸ்ஃபர் ஆஃப் proton into the intermembrane phase. But ஆனா மூணு சிஸ்டத்துல மட்டும் தான் என்ன ஆகுது, protons are transferring. So there are two different starting pathways. One is the succinate dehydrogenate pathway that is present in the complex 2. Another one is a NADH redox partner, which is along with the FNM. It will act as a one more pathway. These two pathway produces electrons as well as proton, what we have seen. So they are connected to the quinol, ubiquinol and ubiquinone. Ubiquinone receives the electron from several different electron carriers and gets reduced. It will undergo immediate reduction. Upon reduction, it passes the electron to the complex 3. So it will takes up. So what would happen once the ubiquinol is reduced? It immediately undergo oxidation and it will transfer the electron, and the cytochrome B, which receiving the electrons which is coming from the quinol, that will be converted into cytochrome B reduced form. Here also we are having a 1 iron sulfur protein, so from which the electrons are transferred to cytochrome C. This complex is accompanied by the oxidation of ubiquinol that we have seen, the reduction of 2 molecules of cytochrome C. 4 hydrogens are pumped across the membrane to the intermembrane space. So already we have seen that one, right? Yeah, here you can see upon complex 3 reduction, 4 electrons are pumped into the intermembrane space. Cytochrome CP1, BC1 is a complex that is a homolog of cytochrome BF. In the case of animals, we will have cytochrome BC complex, whereas in the case of plants, we will have cytochrome BF complex. Here what we have seen, cytochrome B we are mentioning now, it is a complex form of 2 cytochromes will be present. One is the cytochrome B along with the cytochrome F, and some cases cytochrome BC1 will be present. So what it will do, it will transfer the electron from quinone to cytochrome C in the case of animals, whereas in the case of plants, what would happen, from quinone to plastocyanin they will transfer the electrons in the case of plants. This is the important thing. The BC1 complex வந்து இங்க வந்து 2 different kind of இதுல தான் இருக்கு. ஒன்னு வந்து என்ன ஆகுது, இங்க இதுல வந்து என்ன சொல்றோம், ஃபர்ஸ்ட் கேஸ்ல வந்து they are transferring electrons from quinone to cytochrome in the case of animals, whereas the quinol to plastocyanin வந்து போச்சுன்னா அது வந்து that is in plants electron transferring pathway. So next is the complex 4. Complex 4, there are 2 protons are pumped from the matrix to the intermembrane space and formation of water is accomplished. Here is the presence of cytochrome C oxidase is there. Cytochrome C is the copper iron couple which is involved in the O2 activation as well as the reduction of O2. So as we said, the catalysis is the 4 electron reduction of O2 and 2 molecules of water. It requires 4 proton and 2 among the 4 proton, 2 protons are consumed and 2 protons are transferred. 1 molecule of O2 is reduced and 4 electrons that carried by the cytochrome C result in the formation of net transport of 2 protons. Here you can see 4 cytochrome CP is there, that will in the presence of 4 proton, it is reducing the water molecule into the oxygen into water molecule. So complex 4, finally the electrons are transferred to the oxygen and 2 protons are pumped across the membrane. A total of 10 protons are pumped across the membrane per molecule of NADH. So molecular oxygen is diatomic and hence 2 pairs of electrons are required along with 2 cytochrome C complex to complete the reaction. So a pair of electron as well as 2 cytochrome C oxidases complexes are required for the complete reduction of O2. This step is significant as it ensures the continuous removal of electron from the system. இது வந்து நடந்துகிட்டே இருந்தா மட்டும்தான் என்ன ஆகும், இந்த பம்பிங் வந்து கரெக்டா வந்து எலக்ட்ரான் பம்பிங் வந்து கரெக்டா போய்கிட்டு இருந்தா மட்டும்தான் the biological process will gain energy, otherwise it won't gain energy. So what would happen if the molecular oxygen is not present at the stage of to accept the electrons? All the electron transport agents are transfer the electron, but the receiving end la வந்து என்ன இல்லனா molecular oxygen la what would happen? Obviously there would be no outlet for electron. A similar situation arises due to the premature leakage of electrons from the electron transporting complex. So electrons வந்து once வந்து oxygen நால gain பண்ணலனா there will be a leakage of the electrons from the chain வந்து that will occur. Such leakage is commonly observed from complex 1, which generates a number of reactive oxygen species. Complex 1 already we have seen, that is a NADH and a FMN. So from that will produces a large number of superoxide radical. That is the highly dangerous one for the biomolecules. Radicals வந்து அதிகமா வந்துச்சுன்னா என்ன ஆரம்பிச்சிரும், automatically that will cause the mutation. So it is estimated that under the physiological oxygen concentration, only 1 to 3% of oxygen is reduced in mitochondria, maybe from the superoxide anion. Some little amount of superoxide may be generated. This low rate of leakage is probably due to the arrangement of electron carriers in the complex that facilitates the movement of electron to the next compound of the. So the presence of all the redox partner is important. Then only they can easily transfer one stage to another stage. If there is no, some of the redox component is absent in the catalytic cycle in between, that will lead to the generation of superoxide anion. So such kind of unwanted reactions are avoided by means of the presence of regular arrangement of the biological engines, and these engines are highly responsible for the O2 reduction. This is also one of the reason why the presence of different electron carriers and shuttling of electron taking between these becomes so important. Once the electron carriers are not present, automatically that is the end point of the electron transport. From that point there is no electron will be transferred to oxygen. In addition to that, if the oxygen is more depletion condition, automatically there is no small molecules to receive the electrons. Then respiratory chain will leak out all the electrons and it will generate the superoxide radicals which are present in the surroundings. So this is highly important. That is the reason why people will ask us to breathe more intense. So once oxygen is entered, this biological process will continuously takes place and supply the needed energy. That is the ultimate aim of the nature. Cyanide as an inhibitor. So as we well known about the cyanide poisoning. So cyanide poisoning வந்து என்ன பண்ணுன்னு பார்த்திருக்கோம், sometimes வந்து that will arrest the respiratory chain. The respiratory chain வந்து எங்க arrest பண்ணும் பார்த்தீங்கன்னா at the end of the fourth complex இருக்குல்ல, அந்த fourth complex is having cytochrome C oxidase. This will undergo strong binding with the cyanide inhibitor. Cyanide is potential poison. We are well known about those things. So cyanide attacks the ion which is present in the complex, thereby inhibiting the cytochrome C activity. So அதை வந்து ரிமூவ் கடைசி ஸ்டெப்ல வந்து என்ன பண்ணிரும், cyanide வந்து cytochrome C oxidase ஓட தான், ஏன்னா cytochrome C oxidase is having some vacant site. அந்த vacant siteல போய் என்ன ஆயிரும், 6th ligand வந்து cyanide will undergo the linear coordination mode la போய் உட்கார்ந்துரும். iron, carbon and nitrogen all are arranged in a linear manner. So அப்படி இருக்கும்போது அந்த strong interaction-னால என்ன பண்ணிரும்னா cytochrome C will be oxidized immediately and it won't undergo further electron transporting to molecular oxygen. It binds so tight that no electrons and oxygen can be bound to the cytochrome C oxidase. So electron transport is reduced to 0. Thus it blocks the electron transport and inhibit the protons from moving into the matrix of the mitochondria. ஸோ சைட்டோக்ரோம் சியோட அந்த ஏதாவது அந்த செயின்ல வந்து ஏதாவது ஒரு இடத்துல கட் ஆனா என்ன ஆகும், அந்த செயினோட ஸ்ட்ரென்த் ஆட்டோமேட்டிக்கா தட் வில் diminishes. The proton gradient is disturbed by ATP synthesis and ATP synthesis வந்து என்ன ஆயிரும், ஸ்டாப் ஆக ஆரம்பிச்சிடும். ஏன்னா வந்து கடைசியில் வந்து O2 should be reduced to water, that will releases energy. So if it is not releasing energy, then ATP synthesis also stopped. See here, this is what, yeah, this is all about the cyanide poisoning, which is taking place in how it is affecting the respiration. How to treat the cyanide poisoning? For that we can immediately do something. So injection of amyl alcohol or inhalation of amyl nitrate. If you are doing such thing, what would happen? The hemoglobin will be converted into methemoglobin. The methemoglobin has having higher tendency to bind with the cyanide ion. ஏன்னா methemoglobin வந்து iron என்னவா மாறிடும், +3 oxidation state க்கு மாறிடும். அந்த +3 oxidation state ல இருந்து என்ன பண்ணும், that will undergo strong affinity towards the cyanide ion and takes up the cyanide ion back from the cytochrome C active site. So then immediately the cytochrome C oxidase activity will be revoked and it will do the function. This is about the cytochromes and how the electron transport is taking. A total of 10 protons are pumped out during the course of 1 molecule of O2 reduction. That we should keep in our mind. Next one is the cytochrome P450. It is also a heme protein which is involving in the terminal oxidase of the mixed function of electron transport system. That is nothing but cytochrome C. It is one of the enzyme which is responsible for the oxidation ability of the organic substrate. So the oxidation ability எப்படி இதுக்கு generate ஆகுது, electron transferring system ல இருந்து after accepting the electrons, this will undergo some kind of auto activation. Located in stomach endoplasmic reticulum of a small of all major organs and tissues. It uses NADPH as a source for proton, and this is the active structure of cytochrome P450. It is adopting a 5-coordinate geometry. Here you can see cytochrome P450 is having one thiol sulfur, cysteine thiolate sulfur, and a heme B structure is also present here. Heme B, it is having heme B, 4 methyl groups are there, 2 vinyl moieties are there. There is no covalent interaction between the protein as well as vinyl group. Only it is undergoing interaction via the protein cysteine sulfur residue. This is the 6th position which may be occupied by the water molecule. The water molecule is replaced upon catalysis. This is the catalytic cycle which is followed by the cytochrome P450 enzyme. In the resting state, iron is in the +3 oxidation state. Wait a minute. Some other slides will be better for you. Here you can see this is a resting state. Here it is having the heme B structure and axial thiolate moiety and one water molecule. This water molecule is replaced upon the active site activation. We well know that it is involving in the O2 activation. So iron is in the +2 state. It is not suitable for O2 attack. So what we should do, the iron should be reduced to iron 3 to 2. Then only it will bound with molecular oxygen. The first step, what is happening? The substrate, while approaching the active site, when it is come closer to the active site, the water molecule will be removed from the coordination environment. The iron will undergo spin state change also. When we are having a 6th ligand, water as a 6th ligand, it is a high spin ferric form, whereas in the 5-coordinate geometry, the square parameter geometry, whenever it is adopted at the time, it is a low spin state to high spin state is switch overing. The axial water ligand is removed, then the field experienced by the iron center will be very less compared to these two geometries. Under this environment, iron is in the low spin to high spin state. It is switchover. So it will accept the electron which is coming from the electron transporting molecules, and iron 3 to iron 2 will be formed. So iron 2, once it is formed, it is a highly suitable for O2 binding. So here also iron is present in the high spin state only. Once molecular is oxygen is approaching, again it will be converted into high spin, sorry, low spin iron 3 superoxide species. Here what is happening, for initially it is in the low spin state, while we are just changing the geometry from octahedral to square pyramidal, it is adopting a high spin state. Upon reduction also, it is changing the oxidation state and retaining the high spin state. While the sixth coordination position is occupied, at the time, the iron 2 will transfer the electron to molecular oxygen, and molecular oxygen is reduced, whereas iron center is oxidized, and again the spin state is changing from high spin to low spin state. So the second electron also coming from the some other sacrificial reagents, and it will convert the superoxide into iron bound peroxide. Here you can see it is a terminal superoxide, whereas it is a side on peroxide. Here also the spin state is maintained as low spin state only. So this will undergo proton addition, and it will generate a hydroperoxide intermediate. Once the hydroperoxide is formed, that is not at all stable, that will undergo homolytic cleavage of the O bond, and it will generate a iron 4 oxo porphyrin radical cation. Here the beauty is that the porphyrin ring system, which is also redox active molecule, that will undergo oxidation as well as reduction. So that will leads to the oxidation of porphyrin ring system also. So initially people believe that the iron 3 to iron 5 is the proposed iron 5 oxo is the proposed intermediate, but careful analysis of the spectroscopic data, especially mass Bayer, that clearly revealed that iron is in the +4 oxidation state, and in addition to that the ring system, porphyrin ring system is oxidized. That was given by the spectral evidences. So once the active intermediate is formed, that will undergo addition oxidation of substrate. Already we said na RH group, which is present in the close vicinity of the your enzymatic catalytic cycle. So that will abstract the hydrogen from the alkane. The alkane will then generate a radical. That radical will undergo rebound with the iron bound hydroxide. That hydroxide will be transferred to this radical. That is shown here, I think. Yeah. Here you can see. So once substrate is present, substrate is donating the proton. That means the iron 4 oxo porphyrin radical cation is abstracting the proton from the substrate, and it is reduced to iron 4 hydroxyl radical. This is known as compound. So the designation is not clear here. I will show the designation correct. Which one is compound 1, compound 2, and compound 3, and common other 0. So this will also undergo homolytic cleavage, and it will regenerate the active site structure, and enzyme bound product is present that will be ejected from the active site by means of water molecule addition. This is the way how the catalytic cycle is performing in the alcohol oxidation, substrate oxidation. So hydroxylation is done by the cytochrome P450 enzyme. Wait a minute. Here you can see this is a compound 0 is nothing but your iron bound hydroperoxide, whereas the compound 1 is nothing but iron 4 oxo porphyrin radical cation, whereas the compound 2 is iron 4 oxo only. So this will undergo substrate addition with the substrate, that will generate a iron 3 hydroxide. This is recently known as compound 3. Compound 0 is hydroperoxide intermediate, iron 3. This is in the low spin octahedral environment, whereas these are the compound 1 and compound 2 are iron 4 oxo. But in the compound 1, in addition to the oxidation of iron center, the porphyrin is also losing one electron. So it is a porphyrin radical cation. This is nothing but your proton accepted form of the compound 2. Compound 2, once it is accepting the proton, then immediately it will be reduced to compound 3 and it will generate a metal bound hydroxide. This hydroxide is known as, is also now observed as an active oxidant during the course of the catalysis, what we have seen. This is what we have already seen, the peroxo, supraxo, peroxo and hydroperoxo, the cleavage and the formation of the other intermediates. Okay, this is about the cytochrome P450. And the next one is the enzyme which is responsible for yeah. If you are having any doubt, you can ask now regarding that. Next, we will move on to zinc containing enzyme. Zinc, if you are seeing, it is not a transition element. How we can? Why it is not a transition element? Why zinc is not a transition element, pa?
Sir, it does not exhibit variable oxidation state and it is completely filled with d orbital, sir.
It does not utilizes the d orbital for chemical reactions. So only the p orbital and s orbital of the 4s orbital and 4p orbital only utilized for the its reactivity. So it is not at all utilizing the d orbital. Even though it is not at all utilizing the d orbital, but its role in biological system is highly important. In what way? It is having only one common oxidation state, that is nothing but +2. So D10 configuration, if you are seeing the CFSE is almost 0. There is no CFSE. So in this +2 oxidation state, it tends to form a tetrahedral complex. So as we well know that once the CFSE is 0, the coordination geometry also reduced from octahedral or square planar to tetrahedral. It is not at all redox active. Zinc 2 is not redox active. If you are taking the zinc 2 complex and if you want to measure the electrochemical data, if you won't get any response since it does not having the unpaired electron or vacant orbital for electron accept. ஏன்னா zinc 2 to 1 போகாது, zinc 2 to 3 வந்து நமக்கு என்ன நடக்காது, already completely filled D10 configuration இருக்கும்போது. So since the d orbitals are completely filled, it does not exhibit color also. Generally zinc complexes are colorless. Zinc is essential for all forms of life. Adult human containing 3 to 4 grams of zinc. For immune boost up வந்து என்ன தேவைனா உங்களுக்கு வந்து zinc is highly important. ஏன்னா zinc containing enzymes play a major role in digestive system as well as to improve your immune system also. Zinc is highly needed. More than 300 enzymes which are utilizing zinc in their active site. ஏன்னா இது என்ன சொல்லிட்டோம், இது வந்து ஓட்ட ஆக்டிவேஷன்லயோ எந்த ஒரு இதுலயே போகாது, பட் இட்ஸ் biological role is highly important. How it is utilizing its exhibiting the catalytic power? Do you have any idea?
Sir, please repeat the question, sir.
Even though it is not at all redox active, but it is exhibiting some catalytic power. How it is, enzymes are using zinc in their active site and doing the catalysis. So what is the reason for its catalytic ability? How it can exhibit its catalytic power? In what way? எந்த வேலைப்பா பண்ணிருக்கோம்?
Sir, I think the role of zinc is to maintain the structural stability, sir.
But it is also act as an enzyme.
Yes, sir.
Enzyme means it will do the catalysis. In addition to, suppose with the redox active metal ion, if it is present, combinedly present, means it will play a role in structural stability, but it is alone present means it will do the catalysis. How it will do the catalysis? In what way? நம்ம என்ன சொல்லியிருக்கோம் ஆல்ரெடி, if redox ஆக்டிவா இருந்தா தான் then catalysisக்கு வந்து highly suitable-ஆ இருக்கும்னு சொல்லி iron containing enzymes-லாம் பார்த்தோம், காப்பர் பார்த்தோம். பட் வந்து zinc வந்து redox active, it is not at all redox active, but it will do some catalysis. How it will do the catalysis? So understanding the role of zinc is that it is a play major role in the biological system and varying its coordination environment. The most common structural motif in zinc is one is the tetrahedral environment. As we said already, it is mainly utilizing its Lewis acidic power. Okay, Lewis acidic is clear, the tendency to accept the electrons by means of which it will labilizes the bond of the substrate. Okay, va? So it generally having the amino acid residues along with the hydroxyl ligand. Hydroxyl is derived from water. ஏன்னா வந்து catalysisல இன்வால்வ் ஆகுதுன்னு சொன்னோம்னா என்ன சொல்லணும்? It should have a labile coordination site. So அப்படிங்கும் போதுல tetrahedral environmentல இருக்குன்னா 3 donor atoms may possibly comes from the protein donor residue and one may be replaceable ligand system. இங்க பாத்தீங்கன்னா zinc வந்து சாஃப்ட் டோனர் தான். ஸோ இங்க வந்து என்ன இருக்கு? சிஸ்டேட், குளுட்டமேட், இது எல்லாமே வந்து என்ன இருக்கும்? தட் மை அண்டர்கோ பாண்ட் ஃபார்மேஷன். ஹிஸ்டிடின் பாத்தீங்கன்னா இட் இஸ் a borderline நைட்ரஜன் டோனரா வந்து ஆக்ட் பண்ணும் in the case of வந்து புரோட்டீன்ல. These are the commonly observed protein donors which are surrounding around the zinc 2 ion. ஓகேவா? with the tetrahedral zinc 2 plus configuration சொல்லிருக்கோம். tetrahedral environment சொன்னோம்னா இந்த மாதிரி XYZ வந்து protein donors இருக்கா. it may be the any of the combination of the 4 protein donor residues and the fourth site is occupied by water molecule. These are the some of the zinc containing enzyme active site structure: carbonic anhydrase, thermolysin, lysosome, liver alcohol dehydrogenase, amino levulinate dehydrate, and DNA repairing enzyme. Here you can see it is having 3 histidine nitrogen motif, whereas here 2 histidine and 1 carboxylate. Here 2 histidine and 1 cystenyl residue. Here 2 cystenyl, 1 histidine and 1 water. 3 cystenyl residue and 1 water. It is involving in the DNA repair, so it is not having any active replaceable ligands in the active site. So readily undergo complex formation with amino acids and proteins and nucleotides. As far as zinc is concerned, the affinity for thiols and hydroxyl group with electron-rich nitrogen donors also is possible. Approximately 300 enzymes are utilizing zinc in their active site. The biological roles of the zinc is divided into 3 main classifications. One is the catalytic, sometimes it will do the catalysis, and structural, what you said already, the structural stability, it will provide additional stability to the some other active site proteins, and it will regulate the metal ion concentration also. So biological significance, if you are seeing, serving as an essential cofactor along with the some other enzymes, it will also do some act as a cofactor. In the case of superoxide dismutase, what we have seen, we are going to see in the case of the copper zinc superoxide dismutase, in that it will act as a cofactor and it will stabilizes the metal active site. So these are all the enzymatic activity which is exhibited by the zinc containing enzyme. This is the some of the dismutase, polymerase, phosphatase, peptidase, kinase, deaminase, anhydrase, dehydrogenase. These are all the reactions which are catalyzed by the enzymes also. Metallothionein, already we have discussed about metallothionein. Metallothionein is a zinc 2 binding protein which will involve in the zinc storage as well as transport also. So apothionein, when it undergo interaction, at the time it will form the metallothionein. So as we said already, sometimes it will, the bound water may undergo deprotonation and it will produce as the hydroxide. So once the hydroxide is bound, the metal bound hydroxide is act as a strong nucleophile. and it sometimes the OH, which is the the hydrogen which is attached to the water molecule, which also undergo polarization. By means of polarization, it will generate a nucleophile. Or some other cases, the water may be replaced, which is present in the fourth coordination site. So there are three kind of reactions that may be possible for the replaceable water ligand. Water may be either deprotonated or the OH bond may be polarized and it will exhibit the nucleophilic activity towards the substrate, and it may be sometimes it may be completely replaced from the coordination in environment and substrate will bind with the metal. So each and everything we are having example in the carbonic anhydrase and carboxypeptidase, the polarization of the OH bond will take place, and alkaline phosphatase where the water molecule is completely replaced and it will exhibit the enzymatic activity. This is three different ways it can exhibit the catalytic ability. Zinc has a ligand field stabilization energy of 0 in all the ligating geometries, and hence zinc no geometry is inherently more stable than others. Its stereochemical flexibility likely to contribute to catalysis because it can transiently accept different coordination geometry without impeding catalysis. So these are all the three possible geometries. As we said, mainly the four coordination as well as five coordination geometry is mainly observed for the enzyme. So zinc can easily switch over its coordination number between 2 to 8 in general. The most common coordination numbers are 4, 5, and 6. So among these three geometries, the tetrahedral as well as the trigonal bipyramidal or square pyramidal geometry is the common geometry that one can easily encounter in the case of biological systems. So that is not already that we have discussed. So if you are seeing the pKa value of the metal free water is 15.7, but it can be reduced. So while it is bound with the zinc to center, its pKa value is immediately reduced. Higher the pKa means it is not at all readily. What would happen? pKa க்கு என்ன அசிடிட்டிக்கு என்னப்பா ரிலேஷன் இருக்கு? ஹலோ, okay. So carbonic anhydrase is one of the zinc containing enzyme what we are that we are going to discuss now. It is involved in the interconversion of carbon dioxide into carbonic acid, and the reverse it's a reverse reaction. It is a reversible. It will convert bicarbonate into carbon dioxide and proton also. So the forward reaction, what would happen? Carbon dioxide is undergo reaction with water and it will produces the carbonic acid. So consequently, what would happen once the carbonic acid produced that is not at all stable, that will undergo dissociation into proton as well as bicarbonate. Such conversion is aided by the enzyme which is known as carbonic anhydrase. It is a mononuclear zinc containing enzyme. So this is the overall reaction. The first step is the carbonic acid formation. Carbonic acid is undergo dissociation into bicarbonate as well as proton. The first step is the enzyme assisted reaction. The second one is not a non-enzymatic reaction. For this conversion, there is no enzyme is required. But here we need an enzyme to facilitate such kind of conversion. So where it is present in the red blood cell, gastric mucosa, and pancreatic cell and the renal tubules. So what it is doing during the metabolism of food, it will generate carbon dioxide and water. Once the carbon dioxide is produced, the carbon dioxide is and readily dissolved in the body fluid and it will produces the bicarbonate. So the bicarbonate and that bicarbonate will be transferred via blood and it will be excreted, or it may be comes out as a carbon dioxide gas. Gastric formation இருந்துச்சுன்னா என்ன மீனிங்? கார்பன் டை ஆக்சைடோட செக்ரீஷன் அதிகமா இருக்குன்னா உள்ளுக்குள்ள ஏதோ சம் டிசார்டர் நடந்துட்டு இருக்கு. இப்போ அசிடிக் கண்டிஷன் வந்து ஹையரா இருக்குன்னு அர்த்தம். அந்த அசிடிக் கண்டிஷன் வந்து ஹையரா போகக்கூடாம நம்ம வந்து பார்த்துக்கணும். So this is the catalytic reaction. As we said, it undergo the dissociation of the bound hydrogen and it will generate a strong zinc bound hydroxide nucleophile. This nucleophile is having efficiency which is adequate for the carbon dioxide attack. Carbon dioxide is a stable molecule which is having a two double bonded oxygen. So once it is utilizing its nucleophilicity, it will attack the carbonyl carbon, and here the zinc carbon dioxide and hydroxide bound intermediate, the 5-membered ring system will be formed. So in the next step, what would happen? Once the water molecule is approaching the active site, it will expel the bicarbonate ion from the coordination environment. This is the way how the bicarbonate ion is formed by means of your carbonic anhydrase. This is the active site of the enzyme which is having a tetrahedral environment. Zinc is present in the 2+ oxidation state, and it is having 3 histidine imidazole nitrogen donor moiety and facilitating the reversible conversion of carbon dioxide into water. The carbon dioxide and water into carbonic carbonic acid. This is what we have seen. Here you can see. So here one more histidine which is present in the close proximity, which is will act as a base, and it will takes up the proton from the water and generating the hydroxide zinc bound hydroxide. Zinc stabilizes the hydroxide ion and carrying the nucleophilic attack of the carbonate. See here how the intermediate is formed. The 5 coordinate geometry intermediate is formed. Once the nucleophilic attack of the water on zinc, the elimination of the bicarbonate will take place. இந்த ஸ்டெப்ல என்ன நடக்குது? இங்க வந்து இன்டர்மீடியட் ஃபார்ம் ஆகுது. இந்த இன்டர்மீடியட்ல வந்து என்ன நடக்குது? நியூக்ளியோஃபிலிக் அட்டாக் ஆஃப் வாட்டர் ஆன் ஜிங்க். வாட்டர் addition will takes place to the zinc site, and zinc site will expel the bicarbonate ion, and the proton which is abstracted by the histidine nitrogen, that will be redonated, and it will generate the regenerate the active site. So water and histidine, again it will come to the close proximity. This will again abstract the proton, and it will the cycle will continue whenever it is needed. So that is the way we have discussed. Next one is the carboxypeptidase. Peptidase is nothing but it is a peptide digesting enzyme which are known as peptidase. So peptide digest is responsible for the digestion of protein molecules. எல்லா ப்ரோட்டீன்ஸ் வந்து என்னாகும், நம்ம வந்து இன்டேக் எடுத்துக்கிற ப்ரோட்டீன் as well as வந்து பாடியில வந்து பயோமாலிகுல்ஸ்ல இருக்க ப்ரோட்டீன் பயோமாலிகுல்ஸ் ஒன் டீநேச்சர் ஆச்சுன்னா that will releases the protein metal and எல்லாமே ரிலீஸ் பண்ணும். ஸோ அப்படி போகிறதுல என்னாகும், the accumulation of protein will takes place. அந்த ப்ரோட்டீன் எல்லாத்தையுமே என்ன பண்ணணும், சிம்பிளர் மாலிகுலா வந்து க்ளீவ் பண்ணி பாடிக்கு அடாப்டபிள் இதாக வந்து கன்வெர்ட் பண்ணணும், ப்ரோட்டீன்ஸாக வந்து மாற்றணும். ஸோ அந்த வேலையை பண்ணக்கூடியது எல்லாமே peptidase enzyme. So they are classified into 2 types of peptidase. One is the endopeptidase and the exopeptidase. Endopeptidase will cleave the peptide bond which is present in the middle of the peptide links. So அப்படிங்கும்போது வந்து these are all the examples: pepsin, trypsin and hemotrypsin and elastase are the endopeptidase coming under the classification of endopeptidase, whereas exopeptidase having carboxypeptidase and thermolysin. So these can also be further classified whether they are cleaving in the C-terminal peptide or N-terminal. Exopeptidase will cleave the peptide bond at the terminal position of the enzyme. So இந்த terminal வந்து C-terminal cleave பண்ண போதா N-terminal cleave பண்ணுதாங்கறத பொறுத்து வந்து they can be further classified into carboxypeptidase or aminopeptidase. So endopeptidase act in the interior part of the protein, whereas the exopeptidase act on the periphery of the protein molecule. It cleaves the internal peptide bond, it cleaves the terminal peptide bond. End product of the endopeptidase activity is smaller peptides only produced, whereas the end product of exopeptidase activity will produces free amino acids and dipeptides. So these are all the example for the endopeptidase. Carboxypeptidase and aminopeptidase are falling under the category of exopeptidase. So this picture will clearly give the information about the aminopeptidase activity, carboxypeptidase activity, and endopeptidase activity. These two are your exopeptidase. This one is the endo. Endo means interior that will cleave the peptide C double bond வந்து என்ன பண்ணும் cleave பண்ணும். ஸோ அப்படிங்கும் போதுல வந்து இந்த அமைடு லிங்கேஜில் வந்து கார்பாக்சி டெர்மினல் இருக்கிறத கிளீவ் பண்ணும் போதுல இங்கே உங்களுக்கு என்ன ப்ரொடியூஸ் ஆகும், கார்பாக்சிலிக் குரூப் இங்கே ப்ரொடியூஸ் ஆகும். இங்கே வந்து அமைடு இதில் வந்து இதை கிளீவ் பண்ணும் போதுல வந்து இங்கே வந்து இது சிம்பிளர் அமினோ ஆசிட்ஸ் வந்துடும். ஸோ அதனால் இங்கே வந்து என்ன ஆகும், கார்பாக்சிலிக் ஆசிட் டெர்மினல் இங்கே ஜென்ரேட் ஆகும், இங்கே அமீன் டெர்மினல் வந்து ஜென்ரேட் ஆகும். See here, this will give the clear picture. So endopeptidase மூலமா வந்து in between action மூலமா வந்து we are getting two smaller peptide வந்து generate ஆகுது. But in the previous caseல வந்து dipeptide or and amino acids will be generated. Carboxypeptidase structure is shown here. The active site is adopted by the zinc is in 4-coordinate geometry. So two nitrogens in the histidine imidazole donors and one carboxylate donor from the glutamate residue and one water molecule. Sometimes வந்து இதுல என்ன ஆகும்னா இந்த ரெண்டு ஆக்சிஜன் பைண்ட் ஆகிற மாதிரி காமிச்சுப்போம், ஒன்று வந்து வீக் இன்ட்ராக்ஷன்ல இருக்கும். ஸோ the geometry around the zinc 2 is best described as a tetrahedral environment only, not in the square pyramidal or the in between geometry. So it is a digestive enzyme and hydrolyzes the carboxy terminal of peptide bond. So thereby means of it will do the peptide digestion. A tightly bound zinc 2 ion is essential for catalysis. It's coordinated to water, 2 histidine and 1 glutamate residues. This is the enzymatic function. Here you can see it's a peptide. That peptide is cleaved by the peptide bond which is present between the CO and NH group is cleaved by the peptidase enzyme and it will produce the smaller peptides. In human body, proteins are essential molecule in organism and have a multitude of functions ranging from providing strength to bones and tendons, and it is also act as a storage and transportation of metal ions and O2 transport and iron throughout the body, which is all are by protein part. If you are taking the hemoglobin, heme is the active structure where active site where the O2 is going to bind, but the globular protein is there. Protein is nothing but the combination of peptides. Peptides are formed by amino acids condensation. So the body cells, wherever if you are seeing, this body is totally made up of these amino acids. These amino acids are used to construct the proteins needed by our body. Whatever the protein we needed, that is coming from the combination of various combination of amino acids. To break down the protein into the constant amino acids, the cells uses hydrolysis reactions. The protein reacts with the water molecule to produce amino acid and new smaller proteins, which is aided by carboxypeptidase A, which is secreted by pancreas and used to speed up the hydrolysis reaction. So pancreas, liver and spleen, these three internal organs are highly responsible for the food digestion. Food எங்க டைஜஸ்ட் ஆகுது, நம்ம ஸ்டொமக்ல. ஆனா அந்த ஸ்டொமக்ல வந்து டைஜஷனை வந்து ப்ராப்பரா கொண்டு போறதுக்கு வந்து pancreas, spleen as well as liver, இது எல்லாமே சேர்த்து தான் காம்பினேஷன் வந்து தான். அதனால தான் வந்து ஆல்கஹாலிக்கா மோர் ஆல்கஹாலிக்கா இருக்கவங்களுக்கு வந்து டைஜஷன் அவ்வளோ சீக்கிரத்தில் எய்டட் ஆகாது. தட் இஸ் மெயின்லி பிகாஸ் ஆஃப் சச் கைண்ட் ஆஃப் disorder in liver and pancreas and spleen. See here, this is I will come to the mechanistic pathway. This is the way how the mechanism is operating. So zinc 2 ion, the active site, in the active site we are having the 2 histidine, 1 glutamate and 1 hydroxyl ligand. This is a peptide. First of all, it is undergoing interaction with the glutamate residue of the protein chain and thereby making the C double bond with the peptide bond more labile, and the peptide then only it is undergoing interaction with the zinc center. Here you can see initially it is forming a ester linkage like that, then only it is undergoing interaction with the zinc 2 center. At the time the hydroxide is not ejected from the active site. So what would happen while the hydroxide ligand is utilizing its nucleophilicity by attacking the carbonyl carbon of the peptide bond, at the time the CN bond is cleavage is occur. So the CN bond is cleavage means the amine terminal protein will be released, and it is having some keto-ester linkage. The keto-ester linkage now it is undergoing rearrangement by means of the coordination changes from the hydroxide. Here you can see the hydroxide is now fully transferred to the carbonyl oxygen, and oxygen zinc bond which is facilitated coming from the carbonyl oxygen is present. Here the hydroxide bond is fully detached. So once it is detached, at the time what would happen? This will be the glutamate residue will be moved away from the ester bond formation. So here the carboxylic acid is produced. Here why? The first step is the ester bond formation, upon which hydroxide will attack the carbonyl carbon and CN bond cleavage will occur. Once the CN bond is cleaved, then the hetoester will undergo interaction via the hydroxyl ligand, and it will form the new bond with the oxygen which is coming from the carbonyl oxygen. So at the time the hydroxide group is fully transferred to the substrate. So once it is transferred, at the time the glutamate residue which is attacked in the first step will be relieved from the coordination environment. It will generate the product by means of the water attack, and water attack will leads to the active site generation. Thermolysin is also another one of the important protein which is also involved in the protein digestion, which is also using zinc in the active site of the enzyme. So it is using the calcium ion for structural stability of the thermolysin. It is a thermostable neutral metalloprotein. So thermostable means it can be able to withstand for higher temperature. So generally what we have known, when we are increasing in the temperature, the proteins are enzymes which undergo denaturing. Such kind of denaturing can be easily avoided by means of providing extra stability to the protein structure, that is coming from the addition of 4 calcium in the protein units. You can be able to see here, zinc is present, but in addition to that 4 calcium ions undergo some kind of electrostatic interaction with the protein residues, and it is stabilizing the core. Thermolysin is an extracellular enzyme produced by the bacteriocide that can withstand up to high temperatures, more than 60 or 70 degrees Celsius also it can. Hence, thermolysin has a temperature stability that is superior to most enzymes. Thermolysin is classified as a protease which is falling under the category of the aminopeptidase. The term new, it is a endopeptidase as we said already, as the thermolysin, sorry, aminopeptidase only the exopeptidase. Thermolysin is also a example of endopeptidase that will cleave the peptide bond in between the protein. It's a neutral protease enzyme. Neutral protease means it will exhibit catalytic activity at the biological pH. That is a neutral pH of 7. Around 7 only it will exhibit. The term metalloenzyme is appropriate given the necessity of the zinc at the active site and the requirement of calcium to maintain the active site's tertiary structure. Chelating agents deactivate the thermolysin. Suppose if you are adding the EDTA to the enzyme, what would happen? This enzyme EDTA will takes up the zinc 2 ion from the active site, and immediately it will lose its enzymatic activity. Enzyme of this class demonstrate the substrate specificity which require for the hydrophobic amino acids such as phenylalanine as the residue whose amino acid group is cleaved by the thermolysin. If we are seeing the enzyme catalysis, it is similar to that of what we have seen in the case of your carboxypeptidase, but here the secondary sphere protein residues which are not directly involving in the active site construction, that are also highly important. The secondary interactions which are operating in the enzyme surrounding is highly important. இதெல்லாம் எங்க வந்து வந்திருக்கும்? புரோட்டீன் ரெசிடியூஸ்ல வந்து அன்பவுண்ட் குரூப் இருக்கும் இல்லையா? These groups will also facilitate the speed of the catalysis. என்ன பண்ணும்? இந்த பாண்ட் எல்லாத்தையும் போலரைஸ் பண்றது as well as வந்து பேஸா ஆக்ட் பண்றது, இது இந்த புரோட்டான் டோனர் ஆக்ட் பண்றது, இந்த வேலை எல்லாமே என்ன பண்ணும்? These enzymes will, these protein donors will assist. இங்க பாத்தீங்கன்னா வந்து இமிடசோல் இருக்குது வந்து இமிடசோலியம் கேட்டயானா இருக்கு. ஸோ அப்படிங்கும் போதுல வந்து இட் வில் ஆக்ட் அஸ் அ புரோட்டீன் டோனர். அது இது இமிடசோலேட்டா இருக்கும் போதுல வந்து என்ன, இட் வில் ஆக்ட் அஸ் அ பேஸ் ஆக்ட் பண்ணும். ஸோ அப்படிங்கும் போதுல டூயல் ஃபங்க்ஷன் கேன் ஆல்சோ பி எக்ஸிபிட்டட் பை த அன்பவுண்ட் ஸ்பீசிஸ். ஸோ அன்பவுண்ட் ஸ்பீசிஸ் இஸ் ஹைலி இம்பார்ட்டன்ட் டு லெபலைஸ் த பாண்ட் அண்ட் மேக் த கேட்டாலிசிஸ் மச் ஃபாஸ்டர். இங்க வந்து மெட்டல் ஆக்டிவ் சைட் இருக்கிறதுனால மட்டும் வந்து உங்களுக்கு என்ன ஆகிறது இல்லை, ஸ்பீட் ஆஃப் த ரியாக்ஷன் வந்து இன்க்ரீஸ் ஆக போறது கிடையாது. பட் பை மீன்ஸ் ஆஃப் த பிரசன்ஸ் ஆஃப் residues which are not involving in the, which are not present in the primary coordination sphere, the secondary sphere protein residues will definitely assist the reaction. This is what we have shown already. That's it. That is about the, yeah almost that is over. I think already almost I think I have given only thing is that the vitamin B12 is there, that I we need some. Otherwise it is not at all covered. I think this is the last class for bioinorganic chemistry, so I will share the slides which are not covered. If you are having any doubt, you can ask now. Any doubt?
No, sir.
Okay, pa. Since there is no doubts, better I can stop here, and thank you so much for your kind attention.